And what will they burn instead of coal? Water, replied Harding. Water, cried Pencroft. Water as fuel for steamers and engines. Water to heat water. Yes, but water decomposes into its primitive elements, replied Cyrus Harding. Water will be the coal of the future. The Mysterious Island by Jules Verne. Verne imagined a future where hydrogen could replace carbon as a primary energy resource. If this hydrogen is produced via water electrolysis from emissions-free electricity, then it's called green hydrogen. Hydrogen has many applications, such as mobility and transport, energy storage, and also as a raw material for petrochemical processes and iron making. In this project, I will review two different technologies and their respective life cycle costs. Hello, my name is Satiel Vega. This is the life cycle cost assessment that I will do in benchmarking for electrolyzers. In this video, I will cover the next topics. I will briefly explain efficiency terminology for water electrolysis and then compare two commercially available technologies for industrial scale electrolysis. Talking about the efficiency, we need to calculate the ideal energy that is necessary to do electrolysis. On the right hand of the screen, we have the semi-reactions of an electrolytic cell, where water is transformed to hydrogen and oxygen gases. We calculate the ideal cell potential, that it is 1.23 volts. Then we calculate the Nernst. Then we use the Nernst equations and calculate the stoichiometric amount of hydrogen produced at these ideal conditions. However, in reality, no gas evolution reaction occurs until we reach 1.65 or 1.7 volts. Practical cell voltages of water electrolysis in industrial cells are about 1.8 up to 2.6 volts. The values are much higher than theoretical decomposition voltage of 1.23 volts due to high overpotential and large ohmic voltage drop. Also, it depends on the distance between cathodes, the current density, and temperature of the system. Now that we have briefly talked about electrolysis efficiency, here I present two commercially available technologies to produce hydrogen at the industrial scale. As a fact, alkaline water electrolysis is a technology much more old compared to proton exchange membrane water electrolysis, and alkaline electrolysis is much more cheaper compared to PEM electrolysis, but PEM electrolysis is more efficient. Next, I will present the calculated prices of both technologies using data from two public releases. Although water electrolysis is a widely spread process, only a bunch of companies can produce hydrogen at industrial scale in the order of megawatts capacities. Here I calculate two prices for PEM electrolysis and alkaline electrolysis. As a case study, I will request a hydrogen flow for a direct reduction plant. In this plant, we can use either alkaline or PEM electrolysis. Here are some of my assumptions for this economic assessment. And then we have the summary of acquisition cost, CAPEX, and operation cost, OPEX, for these two different options, considering the price of electricity equal to $40 per megawatt hour. Though PEM water electrolysis is 3 times more expensive compared to alkaline water electrolysis, the latter is less efficient. And finally, the results of the economic engineering calculations that reveal the opportunity cost of using energy efficient technology. Furthermore, I prepared different scenarios where the cost of electricity utility goes down up to $20.57 per megawatt hour, considering that emissions-free electricity is used. In conclusions, the OPEX cost of water electrolysis are more important compared to the CAPEX cost, because there is a direct relationship between electrolysis plant efficiency and OPEX costs. And the OPEX cost, and hence the internal rate of return, are very sensitive to the electric energy price. The higher the electricity price, the higher the internal rate of return of using energy efficient systems. And that's it. Thank you.